Today I'm going to be explaining an important article about domain generalization with the title Representation via Representations, Domain Generalization via Adversarially Learned Invariant Representations. This paper in 2020 from Berkeley. We investigate the power of censoring techniques. First develop for learning fair representations to address domain generalization. We examine adversarial censoring techniques for learning invariant representations from multiple studies or domains, where each study is drawn according to a distribution on domains. The mapping is used at test time to classify instances from a new domain. In many contexts, such as medical forecasting, domain generalizations from studies in populous areas where data are plentiful to geographically remote populations for which no training data exists provide fairness of a different flavor not anticipated in previous work on algorithmic fairness. This topic is very important as well. We study an adversarial loss function for K domains and precisely characterize its limiting behavior as K grows, formalizing and proving the intuition backed by experiment that observing data from a larger number of domains helps. The limiting results are accompanied by non-asymptotic learning theoretic bounds. We obtain sufficient conditions for good worst case prediction performance of our algorithm on previously unseen domains. Finally, we decompose our mappings into two components and provide a complete characterization of invariance in terms of this decomposition. So we model the problem through the lens of a hierarchical Bayesian approach that is extensively used in applications. To study the performance of the proposed approach on a newly coming domain, it is crucial to understand the behavior of our adversarial loss in the limit of large K and n sub i's. However, the structure of discriminator changes with growing K, thus a crucial challenge lies in pinning down whether our loss admits a limit, and if so, what should be the limiting value. Additionally, even if we can characterize this limit, how would the proposed algorithm perform on an arbitrary D? So the formal setup is that we have a set of seen domains, for example, K domains, but we have a collection of observed samples. So K different sets of observations. For any function G and distribution D, we use G of D to denote the distribution of G of Z, and Z is drawn from our domain. For any distribution D that admits a density, so all of them are standard, and F is just a mapping from Rm to Rn. The samples are first passed through an encoder that produces a presentation of the input covariates. So phi is a representation mapping that belongs to some function class. The output from the encoder is subsequently passed through a discriminator. So this psi k is our discriminator, and this zeta lies in some function space, function class. To the encoder, discriminator, and predictor will be simultaneously trained using a loss function that comprises two components: the loss corresponding to the predictor and the loss corresponding to the discriminator or adversary The form of these loss functions is inspired from this reference. So we have predictor loss, adversarial loss. But we need the empirical version of that because we don't know the real probability. So this is the approximate, empirical. So we seek to optimize this loss to obtain the infimum supremum of L. The infimum aims to maximize accuracy of the predictor, while the supremum ensures the performance of the discriminator is minimized. And the final predictor for any test data point is given by y hat. Recall the definition of H divergence. Let H be a class of binary classifiers. Then H divergence between distributions is defined here. So then we can see that this sum is 1 plus p minus p. So drawing from the first, drawing from the second. So we are relating it to this H divergence. Our loss is natural generalization of H divergence and has a straightforward interpretation. How best can the discriminator distinguish the images from the K domains? Here we have the theorem that suppose M is a probability distribution and each of which is a distribution over the product space. So we draw these domains from mu with corresponding study their identities, IIDs. Then under this assumption that it is continuous and has non-zero volume, we can say that the lim max is the supremum of the sum of the probabilities. And the probabilities on the left-hand side are taken with respect to marginal covariate distributions of the scene domains. But the right-hand side contains probabilities with respect to the corresponding marginals of the distributions. So the theorem says that for every phi, as K grows, the encoding contains repeated instances of every element. So the limit may be viewed as a measure of dissimilarity of the set. We now turn to bounding the generalization error. So we define L like here, and then define G to be this set. The elements in G form a partition, and the intersection of every pair of elements has volume 0. This definition is important. An element phi is said to be invariant representation mapping for a collection of K domains if the supremum of the probability of composition of pi and psi is less than epsilon. Recall that the range of an phi, so that phi can be expressed in the form. Suppose that the space containing phi is separable. That is, there exists a basis function. These are the basis function that you can linearly write. It's a linear combination, but M could be infinity as well. So it's when we say separable, it's just it could be anything. M could be infinity as well. So the sum could go forever. One defining On defining the matrix M, we have phi, and let gamma be this one, and denote M inverse to be MP inverse of M phi. Here they characterize the invariant mapping, that there exists some f in the kernel of M such that this probability, the sum of these probabilities is less than epsilon.